Welcome to Ask and Learn.
For this problem, the first thing that I noticed is that we have an n on top and we have a 1 plus n at the bottom, and then we have an n as the exponent. So that reminds me of this fact. That this limit is 1 over e. Usually we see it the other way around. Limit as n approaches infinity of n plus 1 over n to the power of n is e. But certainly if you take the reciprocal of the limit, then you get the reciprocal of the answer. So this reminds me a bit of this. So it'd be convenient if these guys had the same exponent, because then we could just lump this n over 1 plus n together and take out whatever their common exponent was. So down here we have an exponent of 3n. Up here we have an exponent of 2n. So if we want a common exponent, what we could do is multiply the top and the bottom by n to the n. And then once we do that, then both of these guys have an exponent of 3n now. So if we want, we can pull their common exponent out and get this. Okay, and then as we mentioned here, as n goes to infinity, this chunk is just going to be some finite constant. So in this case, this chunk is going to be 1 over e cubed. Okay, so this is just motivation for what the bn should be when we're doing the limit comparison test. Okay, so this is going to be the an terms. So these are just the terms that we started with. And then the bn terms, you could make 1 over n to the n. Okay, and the bn term should be somewhat close to the an terms in the sense that if we take this limit, we should get something that's finite and non-zero. So in this case, as we mentioned, when we take this limit, what we're going to end up getting is 1 over e cubed. Okay, so it doesn't matter that this is not equal to 1. It doesn't really matter that it's less than 1 either. The important part is that it's something that's finite and it's non-zero. And as long as we accomplish that, we know that whatever happens when we sum up these bn terms, we should get the same thing when we sum up these an terms, the same behavior, that is. So summing up these bn terms from n equals 1 to infinity, we're going to get convergence. So therefore, we should get convergence over here. And if you really want to be convinced that summing up these bn terms, you're going to get convergence, what you could do is compare it to one over n squared. Right, 1 over n squared is always going to be bigger than 1 over n to the n for n equals 1 all the way up to infinity. And these are all just positive terms here. So if summing up the bn terms is less than summing up the 1 over n squared terms and everything's positive and 1 over n squared terms converge, then these guys must converge, and therefore the an terms must converge by the limit comparison test. But I think that it should be at least intuitively obvious that summing up these bn terms will get convergence. And if it's not, then you might want to think a little bit more about why that would be. So, I mean, basically, you just want to be convinced that these terms are approaching zero sufficiently fast. And as long as that's happening, then you should get convergence.